Let's start with laws of indices. Now, laws of indices are basically first we understand what exactly are indices. Now, indices are powers of certain numbers, right? So let's say we have a number 5 and then 5 to the power 3, right? Now this 5 to the power 3, 7 to the power 2, they are all indices, right? So some basic laws of indices are, if let's say there is a base a, right, and a to the power m multiplied by a to the power n. Now you notice that the two numbers being multiplied, they have the same base a. The first number is a to the power m, the second number is a to the power n. Then the result is going to be the same base to the power m plus n. So essentially what is happening is that the powers are getting added if the bases are same and two numbers are being multiplied. Similarly, when these two numbers are being divided, right, we get a to the power m minus n, right? So what is happening is that whatever power is getting divided, right, that is subtracted from the power of the quotient. Next, if we have a number of the form a into b, so there are two numbers being multiplied and whole to the power m, then you can write this as a to the power m multiplied by b to the power m, right? So what happens is that m as a power can be given to both a and b. Then a to the power m and whole to the power n is actually equal to a to the power m multiplied by a to the power m multiplied by a to the power m, and this happens n times. This means that a to the power m, when multiplied with itself n times, we get a to the power m into n. So essentially, if there is a power outside of the bracket, it multiplies with the power inside of the bracket, right? Now, a very interesting base is 1, right? So you give any power to 1, let's say 10, it will continue to remain 1, right? Likewise, you give any power to the base 0, right, it will remain 0. So a lot of times these two bases, they are used in special situations. They are handled separately, but for all the other bases, all of these laws will apply. Now if there is a peculiar situation, right, let's say 10 to the power 4, right? Now whatever this number is going to be 10,000, right? Now we can write that 10 will be 1/4 power of 10,000, right? So essentially, if I must generalize this, I can say that this is a special result, that p to the power x, when this equals q, then p equals the 1/xth power of q, right? So this is an important result that we must remember. The next important result that we must remember is that if let's say p to the power x equals q to the power y, right, then we can write p as y by xth power of q, right? So we can take the 1 by xth power of both sides. So we get p on the left hand side and we get q to the power y by x on the right hand side. Likewise, q is equal to the x by yth power of p, right? So this, from this result, we can derive both of these. Then if let's say we have a negative power, right, let's say p to the power minus x, then we can write this as 1 upon p to the power x, right? Next, if we have same base, right, let's say p and p on the left hand side and right hand side, and if somebody tells us that p to the power y equals p to the power q, then we can say that y has to be equal to q because the bases are same, right? Lastly, there is one confusion that students typically face, and it must be clarified. If let's say you have if you have a number like this, 4 to the power 5 squared, please do not make it equal to 4 to the power 5 squared. These two are not equal, right? Why? Because this is 4 to the power 25, right? And on the right hand side we have 4 to the power 10, right? So please do not equate this and this, because this is the power of the power. Here it becomes the multiple of the power, right? So these are some of the basic laws that govern indices. Now there's one important result that you must remember, right? And that is that if let's say you are given two numbers of the form p to the power x minus 1, right? And you are given another number p to the power y minus 1, right? Then it's very interesting that this number and this number, both of them are going to be divisible by a third number. Both are divisible by a third number, p to the power HCF of x and y minus 1, right? In fact, this number, right, p to the power HCF of x and y minus 1 is actually the HCF of both of these numbers, right? Let's take an example. Let's say you have 14 to the power 20 minus 1, okay? And then you have, this is number A. Then you have a number B such that it is 14 to the power 24 minus 1, right? If we were to find the HCF of A and B, then HCF of A and B is going to be 14 to the power HCF of 20 and 24 and minus 1, right? So HCF of 20 and 24 is 4. So our answer is 14 to the power 4 minus 1, right? So this number is the HCF of A and B. Let's move on to surds. Now surds can be simply defined as irrational roots of rational numbers. So if let's say somebody tells me root 4, right? Root 4 is not a surd, right? But root 3, fifth root of 5, seventh root of 2, they are all surds, right? So they are all surds because they are not rational, right? So now let's deal with surds. Now clearly surds, right? Now this is the square root, right? So square root can be written as the halfth or 1 by 2th power of this rational number, right? So this is square root. Square root is equivalent to power half. Likewise, the cube root is equal to the power 1/3. Fifth root of any number is equal to its power 1 by 5, right? So surds are powers in fractions, right? So that's the other way of looking at surds. Now if let's say you have a number which just looks like this, right? So let's say fifth root of 5. Now this is a pure surd. Why? Because it is not yet multiplied by any other rational number. However, if I say that if I give you a number 2 multiplied by fifth root of 5, right? Now this becomes a mixed surd. Why? Because root 5 is now multiplied by a rational number. Okay. Now, for as far as the mixed surds and pure surds are concerned, now we can do certain algebra on surds. For example, addition. Now, addition among surds is possible only if this part, right, the surd part of the pure or the mixed one, they are exactly the same, right? So for example, I may be able to add 2 root 3 and 5 root 3, right? Why? Because this part and this part is same. In fact, 2 root 3 and 5 root 3, they are both called similar surds. So addition is possible for similar surds only, right? So 2 root 3 plus 5 root 3, if I take root 3 common, I'm left with 2 plus 5, so we get 7 root 3, right? However, what I cannot do in addition is something like this. So 2 root 3, I cannot add to 5 cube root of 3. Why? Because this part and this part is not same, right? Therefore, they are not similar surds. Therefore, I'll just have to leave it as it is. I cannot simplify them unless, of course, I find this out and multiply it by 2 and find cube root of 3 out and multiply it by 5 and so simple addition of surds are possible only if the surds are similar. And exactly like addition, we have subtraction. Right? So in case of subtraction, if let's say we were to subtract 5 root 3 from 2 root 3, it is very much possible we get a minus 3 root 3, right? However, if let's say you have 2 root 3 minus 5 cube root of 3, again we will not be able to do anything about it. However, multiplication is a completely different ball game, right? The multiplication bit of surds, it does not require the surds to be similar, right? Let's take an example. Let's say we have 2 root 3 and this one we must multiply by, let's say, 3 times third root of 3, right? So you notice that this time these two surds are not similar. So what we do is we multiply the non-surd part with the non-surd part. 2 times 3, 6, right? Now how do we deal with this? This part, let me rewrite as 3 to the power 1 by 2. And this, let me rewrite as 3 to the power 1 by 3, right? Now, while these powers are different, I can't do much, but is there some way I can make the bases of the power same, right? What that does is that it allows me to bring everything down to the same surd, right? So you notice that this is denominator 2 and this is denominator 3. If I can write 1 by 2 now as 3 by 6, right? I've multiplied this power, right? I've multiplied the numerator and denominator of this power with 3, right? And similarly, here I can do 2 by 6, right? What I've done is, of this power 1 by 3, I've divided and multiplied by 2. Now what I get is the sixth root of 3 to the power 3 multiplied by 3 squared, right? So what I've done is I've taken the 1 by 6 outside, right? And I'm left with 3 cube inside here and 3 square here, right? So I'm left with 6. This becomes 3 to the power 5 whole to the power 1 by 6. So we get 6 into 3 to the power 5 by 6, right? The other way of writing this could be the sixth root of 3 to the power 5, right? So what we can do in multiplication is we can take everything onto the similar surd and then multiply these numbers, right? So multiplication is always possible even if the surds are not similar, and the same thing goes for division, right? So I mean I could run this exact same example but for division. So let's try division. In case of division, let's say I'm trying to divide 2 root 3 by 3 cube root of 3. So exactly like what I did here. So I have 2 and I have 3 to the power 3 by 6, right? Then this thing is getting divided by, we have 3 and we have 3 to the power 2 by 6, right? So 2 and 3 can get separated. So this 2 and this 3, they come here, right? Now this 3 is 3 cube to the power 1 by 6, right? So this is this 3, and this 3 comes in the denominator because this is getting this is dividing this part, right? We get 3 square to the power 1 by 6, right? So this is 2 by 3, and whole to the power 1 by 6, we have 3 cube divided by 3 square, right? 3 cube divided by 3 square, so we are left with 2 by 3 multiplied by 3 to the power 1 by 6, or which we can rewrite as 2 by 3 sixth root of 3, right? So you notice that just like multiplication, we are able to solve for two surds dividing each other even when they are not similar surds. Now, apart from just doing some of the simple mathematical problems around surds, there are certain other things that we can do for surds, right? So surds can help us, we can use these basic ideas to compare two different surds. So let's say we have a question which says find out which is larger, right? Find the larger of cube root of 3 and square root of 2, right? So let's say we have to find out which one is larger, right? Now what we need to do is we need to bring both of them under the same surd, right? So this is 3 to the power 1 by 3 and this is 2 to the power 1 by 2. Now the LCM of 3 and 2 is 6, so we can bring them both down to the surd, which is the power 1/6, right? So we can rewrite this as 3 to the power 2 by 6. I've multiplied and divided by 2, and this one I can divide and multiply by 3, so we get 2 to the power 3 by 6, right? So we have 3 squared to the power 1 by 6 and we have 2 cube to the power 1 by 6, right? So cube root 3, it turns out, is 9 to the power 1 by 6, 9 to the power 1 by 6, yes, right, because I've taken 2 inside. And root 2, it turns out, is equal to 2 cube 8 to the power 1 by 6, right? Clearly, left hand side, cube root of 3 is greater than the square root of 2.